So, hello everyone, welcome to IMS GATE Academy. My name is Sourav and we are doing a most expected concept series on heat transfer. Today is the 5th or the 6th session, and till now we have completed all the expected concepts of the conduction chapter. We discussed the most generalized concepts, then we discussed about the for cylinders and spheres, then we discussed the case of heat generation, then we discussed the lumped analysis yesterday, and yesterday I also discussed the concept of fins. So, all in all I can say that in conduction those are the important chapters from where you can definitely expect questions. Although we have not done an intensive question session, we will do it later on. As of now we are focusing on the concepts, and on those concepts itself we will be solving the questions, right. Today on the same trend, we will be starting with a new chapter, and that is convection. Today we will be seeing the basics of convection, and with the series we will be completing the convection as well, and then afterwards radiation and heat exchangers will come. But you know that convection is one of the most important chapters as far as your HT is concerned, and I can very easily say that it is the conceptual chapter. Yes, it is one of the most conceptual chapters that you will come across. So, good evening Nikhil. Right. So, we will start by discussing the basic concepts of convection. So, today's heading will be convection. So, what is convection? So, you know that there are three modes of heat transfer, basically conduction, convection and radiation. Now, I can say one thing, that convection and conduction, as far as these two mechanisms are concerned, they require material medium for heat transfer. You know that heat can be propagated, transferred in three ways, majorly three ways: conduction, convection and radiation. The first two modes, that is the conduction and convection, they require the material medium for their transmission, right. Now, we need to distinguish conduction and convection. Now, you know that conduction can take place, majorly we study conduction in solids, but the requirement for conduction is stationary medium. I repeat, the requirement for conduction to take place is the presence of a stationary medium. The medium should be stationary. So, solids are stationary, so conduction very easily takes place. Now, if the fluids are also stationary, that means if the liquids and gases are also stationary, your conduction may take place. That is not at all a big deal. The thing which separates the convection from conduction is the presence of bulk fluid motion. Yes, in convection there is bulk fluid motion. That means I can say that the material medium, the medium itself moves. There is a case in which there is a microscopic movement of the materials, and then your heat is getting transferred as in conduction. But in convection, the medium itself starts moving, starts traveling, and we can very easily guess or apply our common sense to know that definitely when the medium itself is taking away or transferring the heat, some enhancement is there. Yes, some enhancement is there. On one hand, in conduction, when the medium is stationary, transference is there, heat is getting transferred, but I will say that the pace is not that much. But when there is a case of kind of turbulence is there, the medium is moving around, I can say that heat is transferred in a more enhanced way. So, how much enhanced, in what quantity, all those things we will see later on, but I can say that there is a presence of bulk fluid motion. I can say that in convection there is a presence of bulk fluid motion. Bulk fluid motion. Now convection can be of two types. One can be free and one can be forced. So from the name itself we are able to guess that in forced convection you are forcing the medium to move, and in free convection it is moving out of itself. So let me give you a quick example. For example, there is a hot food that is being served. You want it to get cooled very quickly. So what will you do? You will just apply wind from your mouth. You will give it air from your mouth, yes or no? Or you will put it in front of or beneath the fan so that it gets cooled quickly. This is nothing but your forced convection. You are forcing the heat transfer to take place. But suppose that food has come and you are not in very much hurry, so you will simply leave it to cool it by itself. So that is the case of free convection. How does free convection takes place? It takes place due to the buoyancy effects, or I can say in very simple language, it takes place due to the density difference. In one word, if I have to explain what is free convection, it will take place due to the density difference. Whereas forced convection results in takes place due to a many number of factors, right? So we will see in detail what is the mechanism of free convection, but as of now today our focus will be forced convection majorly, right? So also I can say that there is external convection and there is internal convection. This can also be one of the classification as far as convection is concerned, right? So again we will be starting with external convection only. Pipe flow comes over in internal convection, so that also we will see. So we will see each and every aspect, whatever is important from the examination perspective, right? Now my dear friends, yes, see, actually convection is a very much complex phenomenon. Convection is a very much complex phenomenon. Why? Because it depends on a lot of factors. What are the factors? I can say that it depends on the fluid velocity, it will depend on the fluid property, it can also depend on the geometry of the fluid, it will also depends on, that means temperature of the fluid. So many properties convection depends. So at times it is very difficult to analyze. It is very difficult to analyze that what actually is the mechanism of convection. And in spite of these many complexities, the convection heat transfer coefficient is given by Newton's law of cooling. It is a very complex phenomenon, yes, but in spite of that, it is given by a very simple equation, and that is your Newton's law of cooling. Newton's law of cooling. And obviously you will say that, sir, what is the unit of this? So this I have expressed in watt per meter square. That means I am treating this as flux. You can also multiply this by A and make the unit as watt. Okay. As of now I am keeping in the terms of flux only. So what is Ts? Ts is, let's say, the surface temperature. The surface temperature. What is T infinite? It is the ambient temperature. It is the ambient temperature. and this H is the heat transfer coefficient. It is the heat transfer coefficient. Now, when I am saying that it is very much complex, when I am saying that convection is complex, you will say that surface temperature is very easy to determine. T infinite, that means the ambient temperature, is very easy again to determine. So why it is complex? I cannot see any complexity. Actually, determining the H value is itself a very big, thing, and that is where all the complexity comes about. Determining the heat transfer coefficient is not at all an easy job. That requires some, hard work. So let me explain you a case. For example, that suppose that this is a surface, it is there, it is at a temperature Ts, and from here fluid is coming. Let us say that this is a hot surface and this is the cold fluid. Let us say at T infinite, T ambient temperature. So when it comes to the contact with the surface, what will happen, that this is some layer will be formed. Some layer will be formed. I will explain you how the layer will form, but some layer will be formed. Later on I will tell you that this is nothing but the thermal boundary layer. I will explain you that concept. So just assume that a kind of layer is formed. This is your Ts and this is your T infinite. Okay. So what will happen? You have studied that there is a when a fluid comes over the plate, there is the no slip condition, that the fluid which is in contact with the plate, it will stop, it will assume zero velocity, and that is the reason why we study about velocity boundary layer. Now something like that also takes place over in case of the temperature, and there is a development of thermal boundary layer. We will talk about that, but as of now you know that the layer which is in adjacent to the surface, it will stick with the surface, and when the fluid layer is sticking or when the fluid layer comes to rest, it is not moving. So when this is hot, it will transfer heat to that stationary layer by conduction, and in the subsequent layers, the heat goes through layer by layer, then the movement is also there. This is the bulk movement, this is the bulk motion that I am trying to say. But initially when taking heat, that stationary layer is taking heat due to conduction. That means I can say that when we are studying about convection, there is conduction taking place at the first layer, and then in the subsequent layers convection, that is bulk motion, is also taking place, right. So initial layer mein conduction is taking place, and that is why I can write that Q is equal to minus Kf. Now I have to write F. Why? Because this is the conductivity of the fluid, not of the surface, Kf, and I have to write del T by del Y at y equal to 0. Now why at y equal to 0? At the beginning it is taking place, and del T by del Y. Obviously del T by del Y, for having del T by del Y, it is slope. So for that you need the equation of the curve. All these things are there, but okay. This Q and this Q are same. First the heat is getting conducted, and then subsequently convection is taking place. Now this thing is same as that thing. Obviously whatever when we study steady state, whatever heat is getting conducted will be convected. Okay. So H into Ts minus T infinite. So from here, let us say we know the conductivity of the fluid, and somehow I know the temperature profile. So if someone asks me what is the value of H, I can write this as minus Kf del T by del Y at y equal to 0 divided by Ts minus T infinite. Now obviously the major challenge comes here to determine what is the value of H. That is why I have expressed in terms of all these things, and somehow you will be able to know all the things except one thing. For finding H, you will know what is Ts, you will know what is T infinite, you will know what is Kf, but what is the temperature profile, that remains the most important thing that we need to understand. Because temperature profile is that thing which cannot be predicted very easily. I know I can very easily find what is the surface temperature, I can very easily find what is the ambient temperature, I can very easily find what is the conductivity of the fluid, but what is the temperature profile, the entire game in convection revolves around this. You don't know what is the temperature profile. If you know, then it is very easy. If somehow we can find out, then it is very easy, but this is not at all easy. It will require some hard work. Okay. So this is one relation which is used in many numericals for the gate, and we should try and remember this. Now my dear friends, till now we have at least one idea that when convection is taking place, definitely there is an enhancement of heat transfer. If the fluid was stationary, if only conduction was allowed to take place, then there would be heat transfer, but that means that would be not that much at a faster rate. But when we talk about convection, we basically mean the bulk motion, and that means we say that there is some enhancement over the conduction. So that means there must be something, there must be some quantity which would tell you that how much enhancement is there, how much more or how much times the convection is taking place over the conduction, and that thing is given by Nusselt number. I repeat, that enhancement is explained by Nusselt number. So let us try and learn what is the Nusselt number, and this is the first important dimensionless number that we are studying right now. Nusselt number. Okay. Know that we are talking with respect to the fluid. Right now I am not going into the surface, I am only interested in knowing about the fluid. So let us say this is a fluid layer that is there. This is a fluid layer. Okay, I am showing like this so that you will know that it is a fluid layer. It is having a temperature T1 and T2, and within this only heat is going to transfer. Okay. Let us say this length is L, within a distance of L heat is taking place, and the conductivity of the fluid is Kf. The heat transfer coefficient will be H. I am assuming all these are the properties. Now let us say all the layer are stationary and the heat transfer only takes place due to conduction. So what will be Q conduction? What will be Q conduction when it is stationary? So you will say that, sir, it is Kf del T, Kf del T by A, L. Okay. Now you can, if you want to write A, area you can write, but let us say we are talking only about the flux, so anything is fine. Okay, Kf A del T by the thickness, and now I am making some movement in the fluid is making a bulk motion, that means convection is taking place. So what is the convection? So convection will be H A and del T, H A delta T. So definitely by our common sense we know that Q convection is more than Q conduction. Definitely there is some enhancement over the rate of heat transfer. So how much is the enhancement? How much times the Q convection is more than Q conduction? So I can write H A delta T divided by Kf so this is nothing but H HL by Kf. So this dimensionless number is known as Nusselt number. This number is itself known as Nusselt number. And what does Nusselt number actually tells us? It tells us that how many times the heat transfer has got enhanced due to the convection taking place if conduction was taking place, right? So how much times the heat transfer has got enhanced due to convection over conduction, this is given by Nusselt number. And obviously one thing is clear, that if we want the heat transfer rate to take place at a faster rate, Nusselt number should be high. Nusselt number should be high. Okay. What is the expression of Nusselt number? HL by Kf. This L is the characteristic length, which we have already discussed yesterday. Not yesterday, in the lumped analysis lecture we have discussed. What is Kf? Kf is the conductivity of the fluid. Now similar expression we have learnt in bio number. Bio number was also HL by K, but over there K was of the solid and over here K is of the fluid. So this difference is you should keep in mind. Fine. So this is the Nusselt number. This is all about Nusselt number. Okay. Now my dear friends, let us talk about the boundary layer concept. Let us talk about the boundary layer. See, now we will ask that, sir, which boundary layer? We have studied, we know already we have studied velocity boundary layer in fluid mechanics. So what is the concept of velocity boundary layer? That for example, if a flat plate is there and a fluid comes traveling towards it, so what will happen? The layer of the fluid which is very close to the surface, it will stick to the surface due to the no slip condition, and eventually due to the friction between the layers, one by one, the velocities will be affected due to friction, right? And as such it results in the velocity boundary layer. This is the concept of velocity boundary layer or hydrodynamic boundary layer, whatever you like to say. So basically it is due to the no slip condition. The first layer got stuck and came to rest, and that is why eventually there was the formation of the boundary layer. Here also a similar concept is there, which is known as thermal boundary layer. What is thermal boundary layer? What happens when a fluid is coming with a temperature, for example T infinite, and the surface is there, it is having a different temperature, let us say a hot surface I have kept. So the last layer of the fluid, it will acquire the same temperature as that of the surface, and the farther layers are having ambient temperature. So due to the difference, a region develops, a layer develops, a thermal layer develops, that is known as the thermal boundary layer, and it is the profile of this layer itself that is important to know. It is the profile, that profile is important. It can be linear, it can be parabolic, it can be sinusoidal, exponential, anything. So that cubic, majorly cubic is also there. So that thing is important. Now due to this only, why this is important? Because this is giving you the slope, and due to the slope itself you are able to say that whether the heat transfer is taking place at a faster rate or whether it is taking place at a slower rate, right? All the heat is taking place at the surface to the layer. There is fluid, there is surface, so it is taking, heat transfer is taking place. What is responsible? The temperature gradient is responsible for the heat transfer to take place. Okay. So this is the flat plate that I am talking about, and from here some fluid is traveling with you know the velocity u infinite and temperature is T infinite. So you know that velocity boundary layer will take place, which looks something like this. This is the velocity boundary layer. Also, let us say the surface temperature, the entire flat plate is maintained at Ts. The fluid is having a different temperature T infinite. So due to the temperature difference, there is a profile developed, a layer developed, and that is known as the thermal boundary layer, and this is known as the velocity boundary layer or hydrodynamic boundary layer. So at least we know that both layers are coexisting together, and it would be a very sensible thing to say that the formation of one layer is affecting the formation of other layers. When two things are happening simultaneously over the flat plate, we can very easily say that both the things are somewhat dependent on each other, right? When two things are happening, definitely there will be some comparisons, right? And there should be someone who can compare, some number should be there who can compare both these layers. So that layer which makes a comparison between the two is known as Prandtl number. So what is Prandtl number? What is Prandtl number? Prandtl number is given by nu by alpha. Nu by alpha. What is nu by alpha? Momentum diffusivity diffusivity divided by thermal diffusivity. From the name itself, you are able to make out that momentum diffusivity somewhat is referring to that how momentum is diffused from the flat plate to the fluid. At what rate momentum is being diffusing through this layer, and somewhat this is responsible for the formation of boundary layer. And from this alpha, from this thermal diffusivity, we are able to think that okay, somewhat this is telling me that at what rate heat is getting diffused, and somewhat this is responsible for the formation of thermal boundary layer. I repeat again, from the name itself, nu by alpha, momentum diffusivity, that means it is giving us an idea that at what rate your momentum is diffused, momentum is getting diffused, and thermal diffusivity tells us at what rate heat is getting diffused. Momentum diffusivity gives us an idea about the velocity boundary layer, and on the other hand thermal diffusivity is giving us an idea about the thermal boundary layer. Okay, so somewhat I can say that these Prandtl number these two are giving a very vivid comparisons between the two, that is velocity and the thermal boundary layer. Okay, obviously the units are same, meter square per second, that is why they cancel out each other, and it is a non-dimensionless number. Okay. What is nu? Nu is mu by rho. From your concept of fluid mechanics, you know that this is kinematic viscosity, so dynamic viscosity by density. And what is thermal? What is thermal diffusivity? Alpha, that is K by rho Cp. K by rho Cp. So rho and rho gets cancelled out, and this is left with mu Cp by K. Mu Cp by K. So this is the expression that we all want to remember as far as your your Prandtl number is concerned. Okay. Now see, now look over here at the expression of mu Cp by K. Mu Cp by K. Mu is somewhat dynamic viscosity, and it is giving you an idea about the it is giving you an idea about the velocity boundary layer, that at what rate, see friction is there between the layers. So if friction is there, so momentum diffusivity, and K is nothing but your thermal conductivity. So thermal conductivity is giving you an idea about the rate of heat transfer. You know that thermal conductivity is indirectly is responsible, tells you that at what rate heat is getting transferred. Now for gases, what will, for example, if I say air, or for gases what happens, you know, the numerator and the denominator value are more or less comes out to be the same, and that is why its Prandtl number is somewhat between 0.7 to 1. Okay. That means if you just assume that this is giving me an idea about del by delta T. What is del? Del is the the thickness of the velocity boundary layer, and what is T and what is del T? Del T is nothing but the thickness of the thermal boundary layer. And if I am watching the comparison of the two, so numerator del, denominator del T. So when I am saying that for gases this value is almost equal to 1, so I can say that okay, del and del T are more or less of the same thickness. Now for a highly conducting material, for highly conducting metals, if I consider metals, so for metals the K is very high. When K is very high, then first of all the value will come out to be very less, 0.000 something, and I can very easily say that del T is more than del. For metals, this Prandtl number value comes out to be less than 1, and I can say that del T is more than del. And for some highly viscous oils, for some highly viscous oils, what will happen? The mu will be very high. For highly viscous oil, mu will be very high. So Prandtl number is greater than 1. So I can say that del is greater than del T. So all in all, I can say that there are 3 cases possible, and Prandtl number will give you an idea about the relative thickness of the thermal boundary layer and the velocity or hydrodynamic boundary layer. So this is the second important number that we have discussed. First one is Nusselt number, second one is Prandtl number, and when we discuss about the forced convection, automatically one number is very much important, and that is your Reynolds number. Reynolds number gives you an idea about when the flow will get from laminar to turbulent. It gives you about the nature of the flow. So that is automatically important. So Reynolds number, you know, rho v L by mu. So Reynolds number is rho v L by mu. I can say that is a characteristic length. Now for external flow, L is nothing but the length across which the flow is taking place. For internal flow, it is given by a formula 4 AC by P. Okay. But as of now, I know that this number tells you about whether the nature of the flow is laminar, whether the nature of the flow is turbulent. So as of now, when we are discussing flat plate, three numbers are becoming very important, and that is what? Nusselt number, Prandtl number and Reynolds number. These three numbers are very much important when we are learning about forced convection. When we are learning about forced convection. Right? Right. So what is our challenge right now? What do we want to get? Where we are heading towards? That should be known. Where we are going towards? We want to get what is the profile of this temperature. The temperature profile that I have made, you cannot say. In velocity, in VBL, that is in velocity boundary layer, you know that there are many profiles. You have studied about linear profile, quadratic profile, cubic profile, sinusoidal profile. All those profiles you have studied. Here also there must be, you want to know this profile. Why? Because you remember that you need to find the value of del T by del Y. Slope is important. If you don't know, if you know this value, you will know H. If you know H, you will know the value of Q, and that is the purpose. You want to know about the heat transfer. Okay. Now my dear friends, how do we get the temperature profile? I can derive it, the complete derivation I can do, but that will be not very much important from the examination point of view. That being said, I would definitely tell you that how we are actually getting the profile. What is the method? So the first equation that helps us is the mass conservation equation or the continuity equation. Continuity equation is there, del u by del x plus del v by del y equal to 0. Continuity equation is there, so that will help us give it will give us one equation. Second is the momentum equation, momentum conservation equation, momentum conservation equation. Now where we are applying this? Where we are applying this? This is a flat plate. Let us say this is an boundary layer, laminar region. So here we are taking an element, and in this region only we are applying the mass conservation and we are applying the momentum conservation. For momentum conservation, Newton's second law to start with, and you will arrive at one equation. I am even not writing the equation. Why? Because that is not important for you. You just know this much. And third is, see, these two will give me some idea about the velocity boundary layer, fine, but when I have to know about the heat, the temperature profile, so definitely I have to apply the energy conservation equation. That means this element, that small element that I have taken, I have to conserve the energy, I have to apply the conservation of energy principle, and that will itself give me the third equation. So continuity equation, that is the mass conservation equation, momentum equation, that is the force equation, Newton's second law, and energy conservation equation. All these three equations when I apply over there, I will get, it will give me, again Blase's equation is also there, partial differential equations. So using all those differential equations, no need to memorize that much, using all those conservation equations, ultimately you will get the what is known as the temperature profile. Okay? You will get to know what is the temperature profile. So see, velocity profile you already know that, for example, if I consider the 3-degree velocity profile, it is something like u by u infinite is equal to 3 by 2 y by delta minus half y by delta to the power cube. So this is the most famous cubic profile. This is the most most common, most used profile for velocity, where you can find the velocity at any y. What is delta? Delta is the thickness of the layer. Delta is the thickness of the velocity boundary layer. At any y, you will be able to predict the velocity. That is the nature of getting the curve. That is the nature of getting the curve. Right? And similarly you will also get the thermal boundary layer, and the same nature is there. Okay. So if I have to write the temperature profile, it will be something like this. There the difference is taken, and same we will arrive at the same equation. We will arrive at the same type of equation, except that now in spite of delta there will be delta T. And what is delta T? Delta T is the thickness of the thermal boundary layer. Thickness of the thermal boundary layer. Y at any distance y, and this is the temperature. So just remember that in velocity it is the absolute value, but in temperature it is the difference that we take. And again, this is the most common cubic profile that is there in your thermal boundary layer. So till now what we are getting the idea that we have to study the velocity boundary layer and thermal boundary layer parallelly. You cannot exclude something. Yes, we have to study simultaneously the concept of velocity boundary layer and thermal boundary layer. Why? Because the formation of thermal boundary layer is somewhat dependent on the hydrodynamic boundary layer also. That is the reason that you need to have the concepts of both. And why do we need? Because ultimately we want this equation. How this equation is got? Using all these three equations, Blas's equation, we have arrived at this equation. Sir, what is the benefit? Benefit is that now I can very easily find what is del t by del y. I can find the value of the slope at any y, for example at y equal to 0 or any y, I can find the slope. When I find the slope, if I find the slope, I will be able to get this h value. Once I know the h value, you get to know the heat transfer, heat flux, and that is what your objective is. Now, you know the h value. Now you know the h value. I told you that in forced convection, three numbers are super important, and that is your Nusselt number, Reynolds number, and your Prandtl number. Now there is one equation for flat plate that is very much important, or that is used for getting the h at different positions. Now you will be asking me that, sir, till now you were talking about only one h, that means one heat transfer coefficient value. Now you are talking about h at different locations. So actually the h value that we generally use is the average of all the values. Why? Because at different positions your h is changing. It is a local phenomenon, it's a local thing. At different places across the flat plate, when you travel, your h value changes. When your h changes, your heat transfer also changes. So there must be some, for example, I want to know the heat transfer at some different position. You cannot take a same h value everywhere. There will be different h value. So you have to take the h value at that position itself, and when you know the h, you get the heat transfer, h a delta t. So there must be some equation which gives you the h value at different x. Right? So that is the important equation that for flat plate it is being developed. for flat plate, the equation that is developed is Nusselt number X is equal to 0.332 Reynolds X, it is also local phenomenon 1/2, and Prandtl number is the property of the fluid. So don't write X over here, don't write X in Prandtl number, as it is the property of the fluid. Mu Cp by K, mu property of fluid, Cp property of fluid, K property of fluid, so it's a constant. Okay. Now you will ask, where is H? So nu X, Nusselt number X. Why I have written X? Why I have written Nusselt number X? Because at every X the Nusselt number changes. So this is Hx into X by K. HL by K was the formula for Nusselt number. Since it's a local phenomenon, so I have written Hx into X by K is equal to 0.332 Okay. Now see how H is varying with X, that also I can tell from here. How the H value is varying with X, that also I can tell from here. See, Hx is there, by K is there, this X I will bring it down. What is Reynolds? Reynolds is rho V, V infinite, that means the ambient, rho Vx by mu, rho Vx by mu, this is half, and again 1 by X, I have brought this X over here into Prandtl number 1/3. So this this is X to the power 1/2, this is X, and if you consider all these value to be constant, and if I want to know the variation of Hx and X, so it will be Hx is proportional to X to the power 1/2 by X. So Hx is proportional to 1 by X to the power half. So this is the variation that is there, and clearly you can see from here, clearly you can see that when X increases across the plate, the heat transfer coefficient value decreases, right? So now I was saying you that yes, there is a variation for H and X. How it is varying? Clearly you can see inversely to the square root. So roughly, if I want to say, I can say that when you move across the plate, the H value decreases. The H value decreases, and suppose that after some time, this is the case of laminar, and after some time, this is the case will become for turbulent. So again, the H value decreases. But when you ask me that, sir, why there is a increase? This is the Hx proportional to 1 by X to the power 1/2. This is also the Hx proportional to 1 by X to the power 1/2, or any H, at least it is decreasing. So why in the laminar it is value is low and in the turbulent the value is high? Because turbulent mein H value is high. That is why, you know, due to the turbulence effects, the you know that in the turbulent region more heat transfer will take place. So definitely you are expecting a high H over there. So this is the H versus X plot that you will see. Okay, so now we know that H is inversely proportional to X. So all in all, for your examination perspective, you need to know this value of heat transfer. Now comes the second question. The next question comes is that, sir, from here we know what is the local heat transfer coefficient value. If I have to know that what is the average heat transfer coefficient value. Why average heat transfer coefficient? Because everywhere, whatever question we have solved till now, we have been given only one H value. So it becomes very important thing to get that average heat transfer coefficient value, right? So you can directly memorize it, but still I am telling you how we will get that value. So average average heat transfer coefficient, that is the H bar. How do we get? How do we get H bar? So just assume that this is the plate. So, I have tried to show the 3D view, hope it is looking good. So, this is L, length of the plate, this is the width, this is the thickness. So, what I will do, I know that H is changing from with respect to x, let us say this is your x value, at any x we are trying to analyze. So, it is changing. So, what I will do, I will assume when anything changes, I will assume a strip, of dx length, I will assume a strip, the width is b. So, elemental area will be b into dx. So, if I ask you what is the heat transfer from this dx area, so you will say hx its heat transfer coefficient into area b dx, and let us say the temperature is T, the temperature Ts is maintained throughout, let us say the temperature Ts is maintained throughout, and ambient is T infinite, so Ts minus T infinite, okay. And now if I ask you what is the total, if I want to get what is the total heat transfer, so that means I will assume one single H value, area complete will be B into L, and since it is maintained at the same temperature, so Ts minus T infinite. So, Q total is equal to Qx, but I have to integrate from 0 to L, Qx dx. Then only I will be getting the value of the total heat transfer, okay. So, we have to move to the next page, okay. So, Q total is equal to 0 to L Qx dx, because total heat transfer will be same, okay. This is H bar and this is BL and this is Ts minus T infinite is equal to 0 to L. So, this is Hx and this is B dx, okay, B dx is there. So, here I need not write extra dx is anyway coming, take it. So, Ts minus T infinite. Now, temperature is constant, we can cancel out B and B, I can cancel out. So, H bar is equal to now using this relation, I am able to find out what is the average heat transfer coefficient value, and when you solve this, you will come across, you will get 2 times H x value at x equal to L. 2 times H value at x equal to L. This is the expression that you will get for average heat transfer coefficient. So, all in all, I have just showed you how we arrive at this equation, but if you have to remember or if you have to memorize that what is the average heat transfer coefficient equation, average. So, what is its value? Twice H value at x equal to L. Hx is varying with x, Hx is varying. So, Hx value at x equal to L and you twice it, that is the expression, fine. Now, my dear friends, see, we know this equation that Hx into x by L is equal to 0.332 Reynolds number x to the power 1 by 2 Prandtl number to the power 1 by 3. This equation you already know. Now, if I substitute x equal to L over here in the entire equation, in place of x, if I substitute x equal to L, so into L by Hx by k, sorry, it is Hx by k, very sorry, is equal to 0.332. Now, this will also become Reynolds number at x equal to L to the power 1 by 2, Prandtl number to the power 1 by 3. Now you know that Hx, I can write Hx at L to be H average by 2. I can write this thing. So I can, in this place, I can I can write H bar by 2 so here on I can write H bar L by K, this 2 will go there and this will become 0.664 Reynolds number x L to the power half into Prandtl to the power 1 by 3. This is the equation, this is the equation for the where, you know, when you cover the entire plate, you need only one H average. What is H average? Average heat transfer coefficient. What is H bar? Average heat transfer coefficient. The single value for which covers the entire plate is equal to 0.664 REL half to the power Prandtl 1 by 3. Okay. So these are the things that you have to remember as far as the flat plates are concerned. Okay. Flat plates are concerned. So now we will be learning one last topic. Reynolds-Colburn analogy, and then we can say that we will be covering sufficient concepts. So let's now try to see what is Reynolds-Colburn analogy. Now let us see what is Reynolds-Colburn analogy. See, my dear friends, what is this concept? Actually, you know that there is definitely some connection between fluid mechanics and heat transfer, because velocity boundary layer is developed, thermal boundary layer is developed. There is a connection between the two. There is a relation between the two. Now this analogy actually gives you that what is that relation, how your fluid mechanics and heat transfer are related. When you have to jump from one branch to other branch, what is that equation? This will give you that. Okay. So my dear friends, you know from your concept of fluid mechanics that when fluid is flowing, no slip condition takes place, your velocity boundary layer is developed. So tau at the wall, that means shear stress at the wall, I can write mu del u by del x at x equal to L, sorry, del u by del y, at y is equal to 0. Okay. This is from Newton's law of viscosity. I can use this. Okay. Obviously, some velocity profile will be given to you where u by u infinite, I can write 3 by 2 y by delta minus half y by delta to the power cube. So assume that this is given, del u by del y at y equal to 0, you can very easily substitute del u by del y 3 by 2 by delta into this is the value. If you put over there, you will get 3 mu u infinite by 2 delta. This is the value. Okay. Also you have studied, I can write tau at wall to be Cfx into half rho u infinite square, where Cfx is the local skin friction coefficient. Cfx is the local skin friction coefficient. Local what is CFX? Local skin friction coefficient. So I can equate these two. This equation, suppose this is equation 1 and this is equation 2. So I can very much equate these two. So when I equate these two, 1 is equal to 2, we arrive at one equation. And that is your this is our this equation that we arrive at. Now this is completely from the concept of fluid mechanics. Now from heat transfer concept, you know that Nusselt number X is equal to 0.332, Reynolds number X 1 by 2, Prandtl number to the power 1 by 3. This we know. Now if I divide both sides by Reynolds number X into Prandtl number, so we will get 0.332 Reynolds number X to the power minus 1 by 2, Prandtl number to the power minus 2 by 3. This number is known as local Stanton number. This is known as local Stanton number. Okay. So this I can write STX. And Prandtl number minus 2 by 3. So if I bring here, it will be Prandtl number to the power 2 by 3, and that is equal to 0.332 Reynolds number to the power, local Reynolds number to the power minus 1 by 2. So this from fluid mechanics, this right hand side and over here the right hand side are same. So what I can say? I can say that Stanton number X into Prandtl number to the power 2 by 3 is equal to CFX by 2. Now CFX is the thing which is coming from fluid mechanics, and Stanton number is representative of what? It is representing your heat transfer. Okay, now how it is representing heat transfer? Let us see. Stanton number X is equal to Nusselt number X divided by Reynolds number X into your Prandtl number. Okay, Nusselt number HX, X by K divided by what is Rex? Rho u infinity, rho u x by mu, rho u infinity x by mu into what is Prandtl number? Mu Cp by K. So K and K goes away, X and X goes away, mu and mu goes away. So what is left? Hx by rho u infinite Cp. So once you know about CFX, once you know about the skin friction coefficient, you will be able to, Prandtl number is for a fluid, you already know that. You will be able to know what is local Stanton number. Once you know Stanton number, so local Stanton number you know, so you will be very easily able to get Hx, and once you know Hx, heat transfer coefficient, so you will be very easily able to tell what is the heat equation. Hx you know, heat transfer coefficient you know, temperature difference, and you can tell what is the heat transfer. So this is your Reynolds-Colburn analogy, and this is the connecting link. What is the equation of Reynolds-Colburn analogy? This is the equation. And over here I have told you that how from Stanton number, how from local Stanton number you are able to get the heat transfer coefficient. So this is all about the local, Reynolds-Colburn analogy. So today, my dear friends, I have given you the introductory concepts of convection, what actually happens in convection, and what is our primary aim. Our primary aim is to get the temperature profile. once we get the temperature profile, we are the winners. But that is not easy. We need 3 major equations to get the heat transfer coefficient, that to get the temperature profile. What are that? Continuity equation, momentum equation and energy equation. Then we get the temperature profile. Once we get the temperature profile, we will find del T by del Y. Del T by del Y at y equal to 0. From that equation, we will get H. From H, we get the heat transfer. Okay. This is the correlation. This is the chronology. For flat plate, now from the examination perspective, I have already told you that what equation do you need to memorize. This equation, this equation, this equation, this equation you need to memorize. So, you will memorize this. And this I have told you, Reynolds-Coleman analogy. So, overall this much is data is needed for your flat plate condition. From your fluid mechanics, you know that when Reynolds number is less than 2 into 10 to the power 5, it is laminar, and when it is turbulent, the Reynolds number is greater than 5 into 10 to the power 5. This from the fluid mechanics, you know, this I am expecting. So, today I will be stopping it over here itself. Tomorrow I will be continuing with the concept of internal fluid flow. Tomorrow I will be continuing with the concept of, this is the external flow that we have discussed. Tomorrow we will be discussing about internal flow through pipe, where the concept of characteristic length will be coming. 2 cases will be there, and after that, if time permits, I will be discussing the concept of free convection as well, right. So, I hope things are clear till now. If in case of any doubt, you can leave your comment in the chat box and I will be replying it, right. So, this is it for today. I hope you enjoyed the session. Share it with your friends if you find it useful. Do like and subscribe. Thank you very much. Jai Hind.